All right, hello there. Today is a third lecture in a series on chemical reactions. Today's lecture is called Reactions in Aqueous Solutions. Now, you're probably already a step ahead of me and you recognize that part of the word aqueous is aqua, and you know that that means water, and that's awesome, and I hope that that is the case, and I hope that you catch that. But you also know that this is chemistry, and we have to have working definitions and applications for chemistry. So it's not quite that simple, okay? And we'll talk about that as we go. You definitely have to have aqua or water to have an aqueous solution, but it's a little bit more than that. So let's discuss that and make sure that we understand what aqueous solutions mean and understand that there are reactions, like for instance, we've already learned in this class about double displacement or double replacement reactions. Well, that is an example of a reaction that could take place in an aqueous solution. Let's continue. All right, so we know that water means aqua. We know that water covers 70% of the Earth's surface. We know that its chemical formula is H2O, or 2 atoms of hydrogen bonded to 1 atom of oxygen. What kind of, association is that? Bonding association. We know that that is a polar covalent bond. We know that we have areas of plus charge and areas of minus charge, which gives us polarity. Okay, we know that it has structurally what we call a bent orientation. Okay, we also know, it is said that the adult human body is like 66% water. So it's not surprising to any of us that there, especially living organisms, there would be a lot of very important chemical reactions that would take place in water, okay, or that is aqueous solutions. However, let's just make sure we understand something that I've already said. It's just a little bit, more involved than that, okay? We don't want to overcomplicate, but we don't want to oversimplify. If I have this piece of calcium carbonate or gravel, limestone, and I just throw it in water, okay, have I created, by our definition today, an aqueous solution? Because I thought aqueous meant aqua, which meant water. Okay, well, trust me, you have to have aqua or you're not going to have an aqueous solution. But what I just did in and of itself is a little too simple, okay? This did not instantly create an aqueous solution. So by our definition today, right now, no, I don't have an aqueous solution by our definition. So what is our definition of aqueous solution then, okay? All right, well, for this discussion, so read this with me, it's more than just aqua or water. An aqueous solution is one in which water is a good to great solvent, okay? Well, you can't be a solvent, really, if you don't have a solute, or something that you are what? Something that you are making basically dissociate, or a lot of times you'll see the word dissolve. Now, I prefer the word dissociate because I think all of us know what it means to associate or come together, but when you dissociate, then obviously we know that means to come apart. Well, in our case, in chemistry, what are we coming apart into? Well, we're coming apart often into what we call ions. And by this point in time, you know what a cation is, and you know what an anion is, okay? So our working definition, really, of an aqueous solution is going to be one in which water is causing something to come apart, okay? All right, let's continue. We know, once again, that water has this polar structure. We know that it has plus and minus. We know that we say that water is the universal solvent. Given enough time, we say it will dissociate or dissolve almost anything, right? So it's really, really good at dissociation, which is why I have this little cartoon, which is obviously causing a separation. All right? So I wanted to try to give you sort of a visual, because obviously water is not a grilled cheese sandwich. But this individual is pulling this grilled cheese sandwich apart. Well, let's give that a little bit more real life application. So what if I had lithium chloride? And remember, this is an aqueous solution. You got to see the big picture. We're talking about chemical reactions in aqueous solutions. So we obviously have to have our aqua, but when the lithium chloride is in the water, it dissociates. Obviously, here's our cation and here's our anion. When it dissociates, then by definition, we now have an aqueous solution. All right, now in part, we can get a little help with this by looking at what we call a solubility chart. Now, you're going to learn all about this and you're going to put it to work and you're going to watch a separate video on this and you're going to use it, so just stick with me for now. If I find group 1 elements like lithium, then I see that they are soluble. Are there any exceptions? This says no exceptions. So, lithium chloride would be soluble in water, which means it would dissociate. Therefore, this lithium chloride in water would be or meet our definition of an aqueous solution. Okay, this is the chemistry definition of aqueous solution. Now, what if you were insoluble? Okay, so what if you weren't soluble, you were insoluble? Then what that would really mean is that you would not dissociate. Okay, so therefore, what would we not? Well, we would not consider it aqueous by our working definition right now of aqueous solution. All right, let's continue. Let's give you an example. What about salt? Just good old sodium chloride. Okay, you got a sore throat, your mom tells you to mix up a little sodium chloride water, right, and gargle it. When sodium chloride is placed in water, it will dissociate. Well, what does that mean? Well, you know what that means. That means it will come apart into ions. Well, when it comes apart into ions, you have sodium ions and chlorine ions. All right, now by definition then, what do you have? By definition, you have an aqueous solution. So this is an aqueous solution by our working fundamental definition here in chemistry class. Now, what if I had calcium phosphate? Well, and by the way, let's go back to this just for a second. How do I know? Well, I know because sodium is a group 1 element and there are no exceptions again. So by looking at my solubility chart, I find out that this is very soluble, which means it will dissociate. And what about my calcium phosphate? Well, according to this, I have I have a phosphate. Are there any exceptions? So in other words, is it joined? If it's joined with any of these items, it would not be soluble, but it would be soluble rather. I'm sorry. But right now, that's not what it's joined with, okay? Because if you look at your periodic table, where do you find calcium? Well, it's not a group 1 element, it's a group 2 element. So our solubility table also helps us understand that this is insoluble. Now listen, you don't understand the table fully yet, which I'm okay with, but understand this. This is insoluble, which means it will not dissociate, which means by our working definition, right, this is not aqueous. All right, so I'm not going to make you do any of the naming or anything like that. I'm going to take you straight into a chemical reaction. And I'm not going to, there's no secrets here, okay? I tell you this in class. I'm going to show you a double displacement or a double replacement reaction. And I'm going to show you, though, right now, that I'm going to tell you that I'm going to add aqueous silver nitrate to aqueous sodium chloride. Now listen to what I just said. Aqueous silver nitrate to aqueous sodium chloride. Okay, silver nitrate to sodium chloride. Now, but I told you that it was aqueous. Remember that little AQ that could be in the little parentheses right there? Remember that? Yeah? What am I telling you? Well, if you're thinking as we go here and you're trying to stay with me or a step ahead of me, then you suddenly realize, oh, well, you're telling me that it will dissociate. That's exactly what I'm telling you. I'm telling you that this will dissociate, and I'm telling you that this will dissociate. Okay, I'm telling you that. I'm giving you that information. There's no secrets here. I'm telling you that it is aqueous, and I'm telling you that this is aqueous. So when you look at them, okay, you know that they will dissociate or break apart into ions. So what would that look like? Well, it would look like this. But why do I need you to see this? Because if you understand this slide right here, you understand the discussion up to this point. My friends, this is the definition of aqueous. Now, however, what was the title of the lecture? The title was Reactions in Aqueous Solutions. So, just because you're aqueous doesn't mean we're having a reaction, but we're going to have a reaction here. And as I said, there's no secrets. I'm already giving you some of the information to try to help you kind of navigate through this. This is going to be a double displacement. So you can see that it has dissociated, right? Okay. And what did you have? You had your silver nitrate and you had your sodium chloride, and now I'm telling you that it is going to be a double displacement. Well, you already know what that means. It's just going to be a swapperoonie, right? It's going to be a swapperooie of the cations. So this cation is going to replace this one, and this one is going to replace this one. Now, the question is, how do we know that? And how do we know that that can happen? Well, you are already familiar. Let me go back here. One second, right here. You're familiar with the activity series of metals, right? Well, where is sodium? Sodium is right here. Where is silver? It's right here. So sodium is obviously higher on the activity series than silver. So is it possible for sodium to replace silver? And the answer is yes. Okay. So if that were to happen, okay, so if this were to replace that, then obviously this could also be attracted to that. So what happens then? Okay, well, what happens? Well, what happens is that I can get this and I can get this. Now, I need for you to slow down, and I need for you to go back and pause if you need to pause. I need for you to do whatever you need to do to keep up with me. And sometimes you need to slow down, you need to pause, you need to look at what we had, and you need to look at what we have now. Okay? If we're assuming that this is a double, right? A double replacement, all right? Or double displacement. Now, here's the key, though, to the discussion today. Just because you get this doesn't mean that if something is aqueous in water, okay, but when we look at this, here's what we find out. We find out that all of a sudden we have one product that is no longer aqueous. It's a solid. And we have another product that is still aqueous in solution. Okay, now once again, what are we going to use? We're going to use our solubility chart, right? And so we're going to look at this, and we're going to use this to try to help us figure out, exactly what's going on here. So we have silver and chlorine, all right? So here, we're going to find chlorine, right? And here is what? Silver. Now, what does this say? It says that the halogens are pretty much soluble, but wait a minute. If it joins with a silver, then all of a sudden, it's not soluble anymore. So what happened here is that we had the creation of a solid, or something that we call a precipitate. But the other product is still soluble, okay? It's still soluble. All right, now wrap your mind around that, pause, look at it, go back, look at the equation, think about it a little bit. All right, so we had one product that still remained as ions, but we had another product that became insoluble. And in fact, I'll show you an example of this in class, and it will literally create a solid, it will literally settle out. Okay? All right, so what is a precipitate in this discussion? A precipitate becomes an insoluble item. So what we had is we had a reaction, okay, an aqueous solution, and we had a reaction and we created something called a precipitate, or we created something that was insoluble. Part of our products were still soluble, but part of our products became insoluble. And so that gives us the opportunity to talk about what it means to be a precipitate. Okay? All right, so there's going to be a video link to solubility, and you're going to watch it and you're going to learn more about the solubility table. In general, solubility is the ability to be dissolved, especially in water. Okay? In chemistry, solubility is a chemical property referring to the ability for a given substance, the solute, to dissolve in a solvent. In other words, if you are soluble, you will dissociate. Okay, at least under, there are exceptions, and you'll learn that from the table, but as a general rule, if you're soluble, you can dissociate. All right, so what if you're insoluble? Then you're not going to dissociate. All right, so let's do this to kind of make sure we sort of understand very quickly. I needed for you to understand what aqueous meant. But once you understand what aqueous means, then you understand that this is the definition of aqueous. If I put you in water and you come apart, that is an aqueous solution. Now, what if I have more than one item that I've put together in aqueous solution? Then I could feasibly have a reaction. The reaction that we had here was a double replacement, in which one of our products was still soluble, but the other product became insoluble. So don't make this more complicated than it has to be. Are we going to look at more examples together? Yes. Are we going to talk more together? Yes. But what you have to understand is what aqueous is, and then understand once we have aqueous solutions, we can have reactions that occur in aqueous solutions.